Alright, let's get into the ball stacking problem. Here's a situation. We have a pattern of squares here. Each one of these layers represents a value of n, and obviously this is 4 squared, 3 squared, 2 squared, and represented by this notation for, if you have a particular pile so many layers tall. Obviously, this has infinity. You can't have an infinitely tall pyramid, but however many layers tall, this would tell you the sum of all of your balls. So, or blocks, as in the case of my spreadsheet. Same thing. There's two halves to this. There's a sequence half and there's a series half. And here's the last equation for the series. This is an explicit series equation that will tell us the sum of n squared. Okay, so it's a quick overview of the problem. Here's the series that I'm going to use as my example, 2n plus 1. And of course the n values are already provided, and we go down, looks like to 30. The first step I'm going to do is to populate my explicit sequence with what is actually the summand of this. So that's going to just be 2n plus 1. Remember, my n value is actually here. And I'm just going to enter that and drag it down, so to speak. Double click. Populate that column. And you can see these are all the odd numbers. That makes sense. This is 2n plus 1. We, of course, skip 1. Now, the recurrence relation, we always have to have a seed for the recurrence relation. So I'm going to pull that seed over from column B. I'll show you why I'm going to do that in a second. Otherwise, there should be no references in column C to anything in column B or D or anywhere else. All of the references in C should only be in C after this. That's the point of a recurrence relation. So what I'm going to do is the recurrence relation for odd numbers is simply every other one or add 2. So I'm simply going to say C4 plus 2. And I'm going to drag that down. Hopefully my two columns are synced, and looks like they are. What I mean by sum is I'm simply going to use the values I've gotten over here on this side of the table to create sort of an aggregation. It's sort of this is sort of the recurrence relation of series, and the explicit is sort of like the explicit expression in sequences. It's sort of the analogy. Now, what I'm going to remember, the first term of a series is always equal to the first term of a sequence. So I'm going to just bring that over. It doesn't matter which one you choose, explicit or recurrence, it's the same sequence. So the sum should still be the same. Now, I'm going to increment this. I have to do a little cross-column addition here. I'm going to add this one, right? And I'm going to add that to everything else that has come before it in the series. In this case, it's just 3. And I'm going to bring that down. And this is my sum. Now, my explicit sum, I do a little derivation to get that from here. So I can bring that over real quick. My explicit sum looks like this. It's not hard to figure out if you take a minute just to think about it, what the pattern here is. But I'm going to enter that for my my explicit series equation here. Hopefully I get 3. That's a good sign. And I'm going to drag this down, and I get my running tally for for each step. And what's nice about this is I can delete a section, and it doesn't screw up what's after it. I can sort of get individual ends, right? Whereas if I were to do that over here, it throws the whole thing off. So this is, like I said, this is sort of like the recurrence sum, and this is sort of the explicit sum. Now, how I referenced everything in this table, and I'll check your submission in the same method, but I should be able to change the start value, and everything should track. So as you can see here, as I change this, my explicit sum is correct, and my recurrence sum is incorrect. It's not. It does not have enough information before it to make the proper summation. So that's a strength of the explicit sum.